Hello and welcome to our lesson on inverse functions. This is going to be from section 9.2 in our text. This is one of those fundamental sections that brings in a lot of previously covered topics and then applies to many different areas in mathematics. So you're going to need to recall some of the information, some of the concepts that we've covered previously. I've made a list here of what you need to know before you can fully grasp this section. So I'm going to go through the list of what you need to know for this section and give a brief description of each one of these terms. First of all, a relation. Remember, a relation is simply a set of ordered pairs. The domain and the range, basically the domain are the x's and the range are the y's. Or you could say the domain are the inputs and the range are the outputs. You also need to know what a function is. So remember that a function is basically a relation in which each element of the domain corresponds to only one element in the range. So that's one of those major ideas you need to know. You need to have some graphing techniques. Like you need to know how to create a table of values to graph. And it wouldn't hurt if you know the transformations we've covered. Next, the vertical line test, what it is and what it determines. And you need to know how to do composition of functions. Now, the things that we're going to go over in this lesson, we're going to look at how to find the inverse of a relation. We're going to look at the type of symmetry that a relation and its inverse have, how they're symmetric. We're going to look at how to find the inverse of an equation, what it means to be a one-to-one function, the horizontal line test, what it is and what it determines. We're going to look at how to find the inverse of a function, and then we're going to use function composition to show how to verify that an inverse is correct. For our first example, we're going to look at problem number 1 in the exercise set. Here they've given me a relation. I know it's a relation because it's a set of ordered pairs. What they want me to do is find the inverse of this relation. So before I jump into that, I want to make sure you understand that in this list of what we're going to cover, I'm going to try to start at the top and work my way down and make sure that I cover everything you need to know. So from a relation, we need to know what is the domain, what is the range, and then what does it mean to find the inverse of the relation. So remember, the domain are the x's. Each ordered pair is made up of an x comma y. To find the inverse of a relation, all you need to do is take each ordered pair and switch the x and the y coordinates. So the inverse will start with 8, 7, and then 8, negative 2, negative 4, 3, and negative 8, 8. And that is our answer for the inverse of the relation. So I've made a couple of notations here. I'm going to try my best to drive this point home. The domain, remember the domain are the x's or the inputs. The range are the y's or the outputs. The major concept that you need to get from this lesson is that in order to find an inverse, you switch the domain and range. Okay, so to boil it down, the domain of the original relation becomes the range of the inverse, and the range of the original relation becomes the domain of the inverse. Again, major concepts you need to understand here. For an inverse relation, for an inverse equation, and for an inverse function, the domain of the original always becomes the range of the inverse, and the range of the original always becomes the domain of the inverse. All right, so if you're keeping track, that takes care of covering the inverse of a relation. Now we're going to go to Desmos and look at the symmetry of a relation and its inverse. Using number 1 as our example, if we bring up Desmos, what we want to do is we want to input the relation that was given. And the easiest way on Desmos to input a set of ordered pairs is to add a table. And so we're going to input the x and the y coordinates, each one of the ordered pairs for the given relation. And once you've got that relation entered, the ordered pairs, then we're going to go down to the second input and we're going to add another table. And this is going to be a different color. This is going to be blue. And this is going to represent the inverse relation. So once you've got the original and the inverse input, we want to come over here to the graph and we're going to need to scroll out some so that we can see all of those ordered pairs. And what I'd like you to notice is that the green and the blue dots, they appear to be symmetric, like on a diagonal here. These are symmetric, this dot and this dot, and then these two fold over to here. So now, to introduce you to the symmetry of a relation and its inverse, they will always be symmetric about the line y equals x. So if I input that equation, and I'm going to change some settings real quick, just for fun, you can see that each one of these ordered pairs from the original relation and then the inverse of that point, they're going to have what we call reflective symmetry across the red dotted line. And that's going to be true for every point in a relation and its inverse. They're going to have this reflective symmetry across the line y equals x. That's the symmetry they have, but also that's the way you can tell if you have the correct inverse. If the points have this symmetry, then you know you have the correct answer, because a function, a relation, an equation, and its inverse will always have this kind of symmetry. I like to call it fold symmetry. If you fold on the dotted line, the points should lay on top of each other. And so that's how a relation and its inverse are symmetric. Next example, number 8. Here we have an equation. It happens to be a quadratic equation. And the instructions say, find the inverse of this equation. So if you think back to the previous example that we just did, remember that in order to find the inverse of a relation, you simply switch the x's and y's. The same holds true for an equation. If you want to find the inverse of an equation, every y turns into an x, every x turns into a y. So the inverse equation will be x equals 3y squared minus 5y plus 9. And if you're thinking, oh wait, that seems too easy. Well, guess what? It is that easy to find the inverse of an equation. You simply switch the x's and y's. Now we are going to go to Desmos and look at the graphs to see if they have the reflective symmetry that they should. Okay, so in Desmos here, I've already got my line of symmetry. The first thing I want to type in is the original equation. Y equals 3x squared minus 5x plus 9. And remember I said it's a quadratic equation. There you can see that it makes a parabola opening up. So there's our parabola that corresponds to the quadratic. Now, for the inverse equation, this is one thing that's really nice about Desmos, is it's not a function grapher. In other words, you don't have to have y by itself like you do on a TI-83 or an 84. You can simply type in the equation x equals 3y squared minus 5y plus 9, and it will graph that equation for you. Do you see that it's not a function? It does not pass the vertical line test, but it does help us to verify the symmetry. So if I take the black parabola and fold on the dotted line, it will lay on top of the red parabola. Therefore, I know that this equation is the correct inverse because these graphs are symmetric about the line y equals x. All right, so if you're keeping score, that takes care of finding the inverse of an equation. super easy. Next, we need to talk about what does it mean to be a one-to-one function, and that is also going to incorporate the horizontal line test. So if we're going to talk about what it means to be a one-to-one function and the horizontal line test, the best way to do that, I think, is to just look at an example. Number 27, here we're given a function. It happens to be a quadratic function. And the instructions say, determine if the function is a one-to-one function. So what does it mean to be a one-to-one function? Well, first of all, it means that it has to be a function, which means that each element of the domain must correspond to only one element in the range. Then for it to be one-to-one, that means that each element of the range must also correspond to one and only one element in the domain. In other words, the x's and the y's have to be monogamous. Okay, so what we're going to do then to examine this function to see if it is one-to-one is we're going to go to Desmos. Okay, so here I've got my line of symmetry turned off for the moment because I'm not really testing for symmetry. What I want to do is I want to input the function f of x equals 4 minus x squared, and I want to look at what that graph looks like. Now we know it's quadratic, which means it's going to make a parabola. We can see that it is going to pass the vertical line test. Every vertical line will touch only one time, so this is definitely a function. But in order to test to see if it's a one-to-one function, then you apply the horizontal line test. So what the horizontal line test says, it says if any horizontal line can be drawn so that it touches the graph more than one time, the function is not one-to-one. And remember that horizontal lines have the equation y equals a constant. So if I say I type in the equation y equals -3, that's a horizontal line. I can see that it's going to touch this graph more than one time. And that means that the function is not one-to-one. So what does that mean technically? It means that there's going to be a y value, the y value, say in this case, -3, that's going to correspond to two different x's. And that's not allowed if it's one-to-one. Remember, the definition says that each element of the range can correspond to only one element in the domain. And here you have an element in the range corresponding to two different elements in the domain. Therefore, this function is not one-to-one. It is still a function, it's just not one-to-one. Okay, so what we can say then to answer number 27 is we can say, no, it's not one-to-one. And remember, the reason it's not one-to-one is because it fails the horizontal line test. All right, so what I would like to do for this problem is go above and beyond. Sometimes I like to play the what-if game and say, what if this function was one-to-one? Could we find its inverse? And the answer is yes. First of all, yes, there is a way to make this function one-to-one. And if it is one-to-one, then we can find the inverse, and listen to this, and the inverse will be guaranteed to be a function. So I could find the inverse of this function the way it is, but the inverse would not be a function because the original function is not one-to-one. Man, that was a major concept. Let me repeat that because it's important. If your original function is not one-to-one, then the inverse of that function will not be a function. Super important that you understand that. So, what if, okay, is there a way to make this function one-to-one? The answer is yes. Let's go to Desmos and look at that. So in Desmos, remember, we can clearly see that this function is a parabola and it's going to fail the horizontal line test. So if you think about it, what I want to do is I want to create a graph from this graph that would pass the horizontal line test and, okay, now listen close, and retain the range. So the range are the values that y can be, and the range is from bottom to top. And if I click on this, we can see that the range of this parabola goes from minus infinity up to 4. So let me show you how we can take this graph and eliminate half of it so that we will create a one-to-one function without losing any range values. The very peak of this parabola occurs when x is 0. So what I want to do is I want to look at only the x's greater than or equal to 0. Now in Desmos, the way you do a restriction is you open the keyboard, click the ABC button, grab you a set of braces, and then you simply type in x, click this, greater than or equal to 0. Now look what I've got over here for a graph. I now have half of the parabola. Notice the range is still minus infinity to 4. So I haven't lost any range values, but what I have done is created a function that is one-to-one. This graph now passes the horizontal line test. And what that means, it means now if I find the inverse of this function, the inverse will be a function. All right, so let back up to my list. Again, if you're keeping score, we've talked about what does it mean to be a one-to-one function. Each x can have only one y. Each y can have only one x. The horizontal line test is used to determine if a function is one-to-one. So maybe you want to draw a little arrow like this and say, all right, horizontal line test, what does it do? It tells us if a function is one-to-one. And so now that we know how to recognize a one-to-one function, and I've talked about how you can take a function that's not one-to-one and restrict the domain so that it is one-to-one, now we need to talk about finding the inverse of a function. And I have a technique for finding the inverse of a function. I call it the 3S method. And the 3 S's are substitute, switch, and solve. So let's go ahead and find the inverse of this function that we've got here. So using the 3S method, the first S says substitute. Now what we're going to substitute y for f of x. Remember, f of x means y, so I can make that substitution. Now that I've got an equation in terms of x and y, remember from the previous example, number 8, I said to find the inverse of an equation, you simply switch the x's and y's. So now that I've got f of x in terms of y, now I can find the inverse by simply switching the x's and y's. And the third S is solve. What are we going to solve for? We're going to solve for y. So now I need to get the y by itself. We're going to take the 4 and bring it over. X minus 4 equals negative y squared. The y squared cannot have the negative, so I'm going to need to change the sign. That needs to be positive. But if I change the sign on one side, I've got to change the signs on the other. So now what do we have? We now have y squared equals negative x plus 4, or we could say 4 minus x. And then the last step to get y by itself is to get rid of the exponent. So to get rid of a square, you take the square root. Whatever you do to one side, you have to do to the other. And now we have y completely by itself. And so this is where you can rewrite y in terms of the inverse notation. So the f with the little minus 1, it looks like for an exponent. This is inverse notation. When you see this, you're going to say, hey, that's an inverse function. And the inverse function is square root of 4 minus x. Now, I'm going to throw in a couple more details that I've mentioned before that I need to re-emphasize. and that is that the domain of the inverse is the same as the range of the original. So if we go back to Desmos, remember I said that the range of this function was minus infinity up to 4. So the domain of the inverse should be the same. It should be minus infinity up to 4 with a bracket because the 4 is included. And the range of the inverse should be the domain of the original. And again, if we go back to Desmos, remember what we had to do? We had to restrict the domain so that this function was 1 to 1. So the domain is everything from 0 to infinity. So that means the range of the inverse is going to be everything from 0 to infinity. So if you know the domain and the range of the original function, then you know the domain and range of the inverse function. And now we're going to use Desmos to verify everything that I just talked about. So what I want to do in Desmos first is I want to sketch the graph of the inverse function. I'm going to call it g of x. You can call it whatever you want. And that is the square root of, we have a square root symbol here, square root of 4 minus x, and then I'm going to turn on my line of symmetry, and if I scroll in and have you look at that, do you see how they have the reflective symmetry, the fold symmetry? If I fold on the dotted line, this piece is going to lay on top of this piece. So they do have the correct symmetry for a function and its inverse. And did you notice the domain and the range of the inverse are what I said they should be? The domain is minus infinity to 4. So if you look at the values that x can be, this graph is going back to minus infinity. And the biggest x can be is 4. The range of the inverse, I said, should be 0 to infinity. And the range are the values that y can be. See, the lowest that this graph ever gets to be is 0. And it's going to continue to go up and increase forever. So the range is going to go up to infinity. So I've got to admit that one problem covered a majority of the information you need to know from this section. And if you're keeping score, we've talked about everything except for the composition to verify the inverse. So what I'd like to do now is do a few more of these, finding the inverse of a function, because that's the meat and potatoes of this, is how to find the inverse of a function. And then we'll finish it off by looking at how to use composition to verify that. What I would like to do next is let's do 3 examples of taking a function and finding its inverse, easy, medium, and then hard. Number 47 here would probably be the easiest example of finding the inverse of a function that you could run into. So again, if you're going to find the inverse of a function, we're going to use the 3s method. We're going to take f of x and we're going to replace it with y. That's the substitute step. We're going to substitute y in place of f of x. And then the second S is switch. We're going to switch x and y. And the third S is solve. We're going to solve for y. So I'm going to bring the negative 1 over. That's going to give me x plus 1 equals 2y. And then if we divide both sides by 2, that'll get the y completely by itself. And then I'll have my answer. So using the inverse notation, we're going to say f inverse of x. Remember, f of x means y. And now this y that we've isolated is the inverse function. The inverse function is x plus 1 over 2. And that is our final answer. Next example, number 49, and let me go ahead and read the instruction to you so you know exactly what the instructions say. It says, determine if the function is 1 to 1, and if it is a 1 to 1 function, find its inverse. So the way that you can determine if a function is 1 to 1 easily is go to Desmos, input the function and see if it passes the horizontal line test. So our function is f of x equals 4 over x plus 7. And then if I scroll out some and recenter, applying the horizontal line test, we can see that every horizontal line that I could possibly draw is going to intersect this graph only one time. Now there is a horizontal and a vertical asymptote, but those are not going to affect this being 1-to-1. That's not going to make it not pass the horizontal line test. So this is a 1-to-1 function. Now to find its inverse, we're going to do the 3S method. We're going to substitute for f of x. We're going to replace it with y. And then we're going to switch the x's and y's. And third and finally, we're going to do the solve for y steps. If I take the x and f it up, what that does is it turns my equation into a proportion. And remember, to solve a proportion, you simply cross multiply. So that's going to make it a little bit easier here to solve for y. So if I cross multiply, that's going to give me x times y plus 7 equals 4 times 1, which is 4. And then you've got a choice to make. You can either distribute the x, or you can divide by x. And I'm going to choose to divide by x. That's going to get rid of the x's, and with nothing to distribute, I no longer need the parentheses. So now I've got y plus 7 equals 4 over x, and now I can finish the job by simply moving the 7 over, makes it minus 7, and I've got the y isolated. So remember, I said now you can use your inverse notation. That is, the inverse function is 4 over x minus 7. And that is one of the correct answers. And if you're thinking, what do you mean it's one of the correct answers? Well, remember back up here where I said you had a decision to make. Let's play the what if game. And let's say, what if you chose to distribute the x? What would that look like? In that case, you would get xy plus 7x equals 4. And then to solve for y, you would move the 7x over, which would give us xy equals 4 minus 7x, and then you would need to divide by x. So do you see, you're going to need to divide by x either way you go, and it doesn't really matter. You're going to get the correct answer either way. Now that this y is isolated, we can say the inverse function is 4 minus 7x all over x. So these answers are different, but they're correct. They're not identical, but they will produce the same graph. And the last example we're going to look at for finding the inverse of a function is number 85. Here we have a rational function. They do want me to verify that this function is 1-to-1, so we're going to go to Desmos, and we're going to input our function f of x equals, in the numerator, x plus 1, and in the denominator, x minus 3. And again, if we recenter that and maybe zoom out a little bit, you can see again that this graph is going to pass the horizontal line test. Again, it does have a vertical and a horizontal asymptote, but that is not going to violate the horizontal line test. So this function is 1-to-1 because no horizontal line that I could draw would touch the graph more than one time. Now, what does that mean again? That means that finding the inverse of this function will produce a function. Do you understand that? The inverse function will pass the vertical line test. We will get a function for the inverse. Now, let's find the inverse of this function using the 3S method. So first S, we're going to substitute. We're going to replace f of x with y, because f of x is y. And then we're going to switch. every y becomes x, every x becomes y, and then we're going to solve for y. Now, this is why I consider this a difficult problem, is because if you notice, there are two y variables, but in order to solve for y, somehow I'm going to have to get those two y's to become one. So this is going to be fun and exciting for me. What we're going to do first is we're going to take this x and f it up. We're going to fraction it up so that I've got a proportion so that I can cross multiply. Now, what is that going to give me? That's going to give me x times y minus 3 equals y plus 1 times 1. But anything times 1 is itself, so that's just y plus 1. And then I'm going to need to distribute the x to get rid of the parentheses. So we're going to have xy minus 3x equals y plus 1. With the parentheses gone, the terms are free to move about the equation. Remember, my goal is to get the two y's to become 1. So any term that has a y needs to be on the same side of the equation. So we're going to take this y and bring it this way. Since the minus 3x does not have a y, he wants to go to the other side. And then we're going to have xy, that's going to become minus y. The negative 3x will become positive when I bring it over, plus 1. Now, look what I've done. Look what I've accomplished. I now have two terms on the same side that both have a common factor. Guess what I get to do? I'm going to factor it. So since they have a y in common, I'm going to factor out the y. That's how we get the two y's to become 1. And what does that leave me? It's going to leave me x minus 1 equals 3x plus 1. And now I'm to the final step. In order to isolate the y, I'm going to divide by x minus 1. Those will cancel. That'll get my y by itself. And now I can use the inverse notation. The inverse function is 3x plus 1 over x minus 1. Now that we've got the inverse function, the instructions also ask for the domain and the range of the function and its inverse. So let's go back and figure out the domain of the original function. Okay, so we're going to put a box around that. We're going to bring that over here. The domain of a rational function, remember that a rational function has a restriction. And the restriction is that the denominator cannot be 0. To find the domain of the original function, we're going to have to find the restriction. The denominator cannot be 0, therefore x cannot be 3, right? Because 3 minus 3 would make 0, so x cannot be 3. So how do we want to write the domain? It doesn't specify whether the domain should be in set notation or interval notation. So what I'm going to do is I'm going to express it in set notation. The domain is the set of all x such that x cannot be 3. Now remember, I said if you've got the domain of the original, you know the range of the inverse. So now I can write the range of the inverse function, and it's going to be the set of all y's such that y cannot be 3. Remember, the domain of the x's, the range of the y's, no matter whether you're talking about the original or the inverse. And so now if we come back to the original function and we want to find the range, there is going to be a y value that y cannot be, and that's going to occur at the horizontal asymptote. And so that also means that you're going to need to recall how to find the asymptotes of a rational function. So many mathematical concepts that we've talked about that you're going to need to have not forgotten how to do. So to find the horizontal asymptote of a rational function, if the degree of the numerator and the degree of the denominator are the same, then your horizontal asymptote is going to be y equals the lead coefficient of the numerator divided by the lead coefficient of the denominator, which in this case would be 1 over 1, which is 1. And you can see by putting that in there that that fits nicely. That is where the horizontal asymptote goes, and so that is the value that y can't be. So for the range in set notation, it's going to be the set of all y such that y cannot be 1. That means y can be anything else. Again, from the graph, notice it goes to minus infinity up to this horizontal asymptote, and then the graph exists again up to infinity. So the y values can be anything from minus infinity to infinity except 1. And now that I've got the range of the original function, now I can write the domain of the inverse. The range of the original is the domain of the inverse. And we can verify all of this information from Desmos. So let's go to Desmos. Let's get rid of that horizontal asymptote. And let's input the inverse function. And I'm going to call it g of x is equal to 3x plus 1 over x minus 1. And again, if I turn on the line of symmetry and zoom in a bit, maybe if I change the color. Let me change him to blue. There we go. So the blue graph is the original function and the green graph is the inverse function. The red dotted line is the line of symmetry, and you can see that these graphs are symmetric. If I fold on the dotted line, you're going to have the graphs lay on top of each other. So this verifies that what I have for the inverse function is actually the correct inverse function because I get the correct symmetry, the symmetry that I expect a function and its inverse to have. Also, if I turn off the original function and examine the domain and range of the inverse, you're going to see that the domain is everything from minus infinity to infinity except for where the vertical asymptote is. And we said that that should be at 1. So if I graph the line x equal 1, I would expect that to be where the vertical asymptote is. In other words, that's going to be an x that does not exist on this graph. That's not going to be part of the domain. And the range was everything but 3. We said the range were all y values except 3. And so if I type in the equation y equals 3, again, you're going to see that that horizontal asymptote fits nicely in the graph. And that means that that's going to be a y value that does not exist on the graph. And so that's a y value that is not in the range of the function. It goes to minus infinity, it goes to positive infinity, but it doesn't exist at the horizontal asymptote. And so this verifies my domain and my range of both the original and the inverse function. Okay, so back to our scorecard. We've talked about everything now up to number 7. We now need to look at an example that shows how we use composition of functions to verify that an inverse of a function is the correct inverse. And the example we're going to look at to do that is number 77. Here they've given us a function and its inverse. We're going to use composition of functions to verify that this inverse function is actually the correct inverse of the given function. The rule says that if I do f composition f inverse of x, I should get only x, and if I do f inverse composition f of x, I should also get only x. So it's got to go both ways. You've got to do the composition f with f inverse and then f inverse with f. And if you don't get only x both ways, then the inverse function is not the correct inverse of the given function. All right, so here's how that works. First, to find f of f inverse, that's going to be f of f inverse of x. And what that says to do, it says we need to take the inverse function and plug it into the original in place of every x. Okay, so here's a visual of what's about to happen. We're going to take all of this stuff and stuff it in here. All right, so what is that going to give us? That's going to give us 2/5 times 5x minus 5 over 2 plus 1. That's what f of f inverse looks like. And then we need to simplify this to see if it simplifies to be only x. So the 2's are going to cancel, and that's going to leave me with 5x minus 5 over 5. Remember, if I multiply at fractions, I go straight across. And the 2's cancel means they divide it and make 1's. So 1 times anything is itself, gives me 5x minus 5 over 5 plus 1. And then notice that the numerator has a common factor of 5. So then what I can do is I can factor the numerator. That's going to give me 5 times x minus 1 over 5 plus 1. And then notice the 5's cancel, which is going to simplify to x minus 1 plus 1. And then plus 1 minus 1 cancel. So all of that worked to get to just x. Now, is that it? No, that doesn't verify that the inverse is correct because I have to go both ways. So the next thing we need to do is calculate f inverse of f of x. Now, what is that telling me to do? This is telling me to take the original function and plug it into the inverse everywhere there's an x. So here's a visual of what's about to happen. We're going to take all of this stuff and stuff it in here, replacing the x in f inverse with the entire f of x function. So that's going to give me 5 times 2/5 x plus 1 minus 5 all over 2. And then I'm going to need to simplify this and see if I get only x. So the first step is to distribute in the numerator. We need to get rid of those parentheses. If I multiply 5 times 2/5, the 5's will cancel and leave me 2x. But then 5 times 1 also gives me a 5. Minus 5 from the numerator, all over 2. And then in the numerator, 5 minus 5 go to 0. So those cancel and leaves me 2x over 2. And then the x's cancel, leaving me only x. Now, since the composition both ways produced only an x, that verifies that this inverse function is really the correct inverse for the given function. And that is how you use composition of functions to verify a function and its inverse. And that's going to do it for this lesson. So if you have any questions or comments about anything that I've covered so far, please feel free to leave those in the comment section below, or you can text me. And thanks for watching.